Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We are with the ninth chapter of microwave engineering, where the propagation of or the transmission of microwave signal, we can say, that has been generated either onto the microwave tubes platform or onto the semiconductor platform, so is to be done with respect to a circular waveguide, a single conductor transmission line here. So we started to see, first of all, what is the basic corresponding to the conventional transmission line called as coaxial transmission line, and next to that we have been just now introduced to the circular waveguides and the propagation of microwaves through it in the previous video. Let us have the solutions corresponding to the wave equations with the help of cylindrical coordinate system in this topic. So here we start with our topic. The topic is titled Solutions of Wave Equations in Cylindrical Coordinates here. So I shall be making it very clear that we shall be addressing the sinusoidal steady state or the frequency domain solution. So I hope it is very clear, the Maxwell's equation, the wave equations into the various domains here. So we shall be going for the sinusoidal steady state type or the frequency domain solutions for the circular waveguide and with the help of cylindrical coordinates here. So very first of all, we shall be getting introduced to or a revision to the cylindrical coordinates here. So for understanding the cylindrical coordinates, we shall have the orientations with the help of only one axis, that it is the z axis. So we assume the z axis is upright, oriented vertically here. So this is the positive z direction, whereas this is the negative z direction, and this is the center that we can call it to be the origin here. So if you have the knowledge of rectangular coordinate system, so the origin, which is the midpoint of the positive and the negative sides of the z axis, is basically the intersection point with respect to the crossings of x, y and z axis here. So from that knowledge we can consider this to be the orientation of y axis into the positive direction, whereas this is the orientation of x axis in positive direction here. So though the x-axis is basically perpendicular to the plane of the paper that involves y and z axis here, x is perpendicular, but in two-dimensional view it is shown to be a tilted line here. So here we have the cylindrical coordinate systems for any general point P expressed either in terms of rho, phi and z, or few of the notations are also using r, phi and z here, where we have rho or r to be radius of the cylinder here. So it is to be imagined a cylindrical shape here which is centered at the z axis here. This is the cross section and this will be running along the orientation of z axis. So this is the uniform cylindrical cross section here. So rho or r denotes the radius value. So it is the distance of the point from the z axis. If the point is onto the center, rho or r is equal to 0 here. So this can be denoting rho or r, and when it is fixed to the cylindrical shape here, so we generally take rho or r to be the value small a here. Now what is the angle phi here? So when we have the rho denoted as like this in general, and at the point of intersection that has been dropped onto the z axis, we consider a line parallel to that of the positive x axis. The angle measured into the horizontal plane is nothing but the angle phi here, whereas whatever the height it has achieved with respect to the position of the origin here, that height is nothing but the z here. So these are rho phi z or r phi z we shall be using in this derivation for the solutions of wave equations using this cylindrical coordinate system here. Now, very first of all, we shall be making the use of scalar form of the Helmholtz wave equation, and now while using it into the cylindrical coordinate system, we can give it to the form. We write 1 upon r, having the partial derivation with respect to the r corresponding to r in multiplication to del r over the vector a scalar function psi here as discussed. This is the first term and it is added to 1 upon r square in multiplication to del 2 psi by del phi square here, and further it is added to the third term del 2 psi divided by del z square. This is equal to gamma square psi here. So let this can be treated as equation number 1. So always and always the wave equations are relating to the harmonics corresponding to the variations into the time and that of the variations into the space dimensions here. So here the space dimension is with respect to the r, phi and z, the three coordinates of the cylindrical coordinate system. So here it is with respect to the second order partial differentials corresponding to the r, phi and z, whereas gamma square in general gives us the information of the propagation, hence it is called as the propagation constant here. Now for the function represented psi here, we shall be using the method of separation of the variables, and solution to this partial differential equation can be expressed or assumed in the form we have psi as the multiplication of r as a function of r small, capital phi as a function of small phi in multiplication to capital Z as a function of small z here, which can be equation number 2 here. Here we have capital R as a function of small r. It is a function of r coordinate only. So I mentioned here it is a function of small r or rho that we have represented into the previous schematic diagram. So only these parameters will be the dependency of capital R will be there. Now capital phi as a function of small phi, it is a function of small phi only, whereas the third term that we have represented capital Z of small z, it is a function of small z only here. So now we have these equations represented, equation number 1 for the Helmholtz equation and the assumed solution into the three terms by equation number 2. Now here we can make the substitution of equation number 2 into the equation number 1 and dividing the resultant by equation number 2, the new equation form will be 1 upon small r into capital R. We have ddr in the bracket, small r in multiplication to dr by dr here. So this is the first term. The second term it will be 1 upon small r square in multiplication to the capital phi here, where we have d2 capital phi divided by d small phi square here. And the third term can be represented as, here I represent 1 upon capital Z in multiplication to the second order differential for the Z here. So it is d2 capital Z divided by d small z square, and the addition of these three terms is equal to, we have gamma square, gamma representing the propagation information here. So while being the functions represented capital R, capital Phi and capital Z to be corresponding to only the coordinates R, Phi and Z, we have been shifted from partial differentials to the complete differential forms here. So let this is equation number 3 that is representing the sum of the three independent terms, which is equal to the constant given by gamma square here. Now the third term, if you concentrate here, so in the cylindrical coordinate system for the circular waveguide, if the propagation of the signal, if we are considering only into the z direction, so this represents the variation into the z direction. So this is giving us the information regarding guide that is having propagation here. So therefore we represent d2 capital Z divided by d small z square is equal to the propagation constant can be given the subscript small g inside the waveguide, small g to the subscript squared here in multiplication to capital Z. So this can be shifted to the right hand side here. So this is equation number 4 here. Now solution to the equation number 4, the form represented just now, can be given as capital Z is equal to, we have capital A, the constant, in multiplication to the exponential e to the power minus gamma suffix g into small z, whereas we add it to the constant capital B in multiplication to the exponential e to the power positive gamma suffix g z here. So let this can be the next equation number 5 here it is. So now the representation gamma suffix g that we have used in previous and equation number 5 here. So here gamma suffix g can be written to the form propagation constant, and this propagation constant is for the microwave inside the waveguide here. Now here if you are inserting gamma suffix g square for the third term into the previous equation, that it is equation number 4 and equation number 3, and multiplying by small r square, we can have the new equation, the next equation number 6 we shall be giving it to. So this next equation is given as, we have small r divided by capital R, ddr in multiplication, it is operating over small r capital R for the partial complete differential with respect to small r here, added to 1 upon capital phi here in multiplication to d2 capital phi divided by d small phi square, minus here we have gamma square minus gamma suffix g square in multiplication to small r square. RHS now can be equal to 0. So this is equation number 6 here. Now if you concentrate on to the second term of the equation number 6 on left hand side, so this is a function of phi only, therefore we can have the equation for the second term only, giving it expression in terms of the constant term that we can represent minus n square here. So by the next step we shall be writing the second term, that it is having the d2 capital phi divided by d small phi square is equal to minus n square in multiplication to capital phi, that has been shifted from the left hand side, that it was in the denominator there. So let us have this equation number 7 to be. So for such a differential equation of the second order, if the solution is to be found, the solution can be of the harmonic function type. We have capital phi given in terms of capital A suffix n into the trigonometric function sine over n phi here. This is added to capital B suffix n into the trigonometric function cosine over n phi here. So let this solution represented for this form can be equation number 8 here. Now in equation number 6, if we replace the term capital phi by small n square into the equation number 6 that we have previously written, and multiplying throughout by capital R, we can have the new form of the equation. The new form of the equation that we write here, small r in multiplication to ddr, which is operating over r, ddr of capital R here, and here we add it to the next term representing square bracket, which involves kc into small r, the combined they are squared in the bracket, minus n square, the square bracket is completed and it is further multiplied to capital R here. This is equal to 0. So let us represent this equation by equation number 9. So here we have the complete differential with respect to small r for the function represented for r only. We have kc we have been using for representation of the cutoff wave number if we have the propagation inside the waveguide here, and the constant term minus n square we have been representing for the second or the middle term corresponding to the 5 items, and the third parameter corresponding to the z, it is giving us the propagation information here. So now this equation by the manipulation as discussed that we have obtained is of very much importance here, so that I outline here. So this equation is the Basils equation. This is the Basils equation and it is of the order of small n here, where we have kc square added to gamma square is equal to gamma suffix g, which is squared here. So this relationship among the propagation constant and the propagation constant itself, kc square, it is in terms of the cutoff wave number here. So this can be the next equation number 10 here. This is called as the characteristic equation of the Basils equation here. So I mentioned characteristic equation. Now if we treat the propagation to be of lossless type, the propagation information will be having attenuation constant alpha is equal to 0. Therefore we can express instead of gamma suffix g only beta suffix g, and it is equal to plus minus square root of, we have omega square in multiplication to mu epsilon minus kc square here. So let this can be regarded as the next equation, equation number 11. Now the solution of the Basils equation that we have written is of the form capital R is equal to capital C suffix n in multiplication to j suffix n as a function of cutoff wave number kc into R here. This is added to capital D suffix n into capital N suffix n as a function of kc into small r here. So let this is equation number 12. This equation is also very important that I outline here. And in this equation we have the notations j suffix n as a function of kc r here. This is called as the nth order Basils function, and capital N suffix n as a function of kc into r here is also called as the nth order Basils function. In order to not having a confusion between the two terms here, this is the nth order Basils function of first kind here, whereas n suffix n as a function of kcr is again called as nth order Basel function, but this is of the second kind here. So using these two types of the nth order Basels function, that is of first kind and that of the second kind, we shall be definitely representing with the help of the graphical plots here. So the final Solution for the Helmholtz equation into the cylindrical coordinate representation is given by, we have psi is equal to, in the square bracket we represent c suffix n into jn as a function of kc into r added to d suffix n in multiplication to nn as a function of kc into r. Both the kinds we have represented here. So the square bracket is completed here, and it is further multiplied to another square bracket that involves an sine of, we have n pi added to capital B suffix n cosine of n pi here. The square bracket is completed and it is multiplied to e to the power plus minus j times beta suffix g into z here. So this is equation number 13 here, and for this equation these two Basils functions are expressed in the graphical plot given as. So here we express the nth order Basils function of the first kind shown in the schematic diagram, where we have the argument of Jn as a function of Kc into R plotted onto the horizontal axis with the values. Here we have 0, 2, 4, 6, 8, we have 10, 12, 14 and 16 here, whereas onto the vertical axis we have the value of Jn as a function of Kc into R here. So the values here, for this to be the zero crossing here, we have minus 0.02, minus 0.4 here, minus 0.6 here. In the positive side, here we have 0.2, 0.4, 0.6, 0.8 here and 1.0 here. So these are the various waves we represent corresponding to the various values of the n here, that is the order here. So here the first wave we can represent for the 0th order represented by j suffix 0. This is of the first order, j suffix 1, second order j suffix 2, third order amplitude has been reduced in sequence, this is j suffix 3. So this is the representation of the Basils function for the first kind here. Whereas in this schematic diagram we have the Basils function of the second kind here. So here we have the argument of nn as a function of Kc into R onto the horizontal axis, and the value of the function, that it is nn as a function of Kc into R onto the vertical axis. So here we have the horizontal readings corresponding to 0, 2, 4, 6, 8, 10, 12, 14 and 16, whereas onto the vertical axis we have the negative values minus 1.2, minus 1.0, minus 0.8, minus 0.6 here, minus 0.4, minus 0.2. Here we have the 0 value. So this is the 0 crossing corresponding to these waveforms that we have represented. The positive side 0.2, 0.4 and 0.6 are also represented. The nth order Basel function here for the first one will be of the 0th order represented by n suffix 0. Next to that we have n suffix 1, n suffix 2, n suffix 3 with reduction into the first amplitude here. Now if the radius represented in the cylindrical coordinate dimension, that it is r. So if r is equal to 0, so however we have Kc in multiplication to r also obtained to the value 0 here. So that time the value of the function that just now we have represented for the Basils function of second kind, this approaches to the value infinity here. So capital D suffix n will be equal to 0. This means that at the value of r is equal to 0 onto the z axis, the field must be of the finite value here. Also, the use of the trigonometric manipulations that we have represented the two sinusoidal terms becomes, we have an in multiplication to sine of n phi added to bn in multiplication to the trigonometric cosine of n phi is equal to, we can make the square root of an square added to bn square here in multiplication to the cosine, which is operative over the square bracket, n phi added to the tan inverse of an to bn ratio. Here the square bracket is completed. In general, this can be represented as capital F suffix n cosine of the function n phi simply. So let us say this is equation number 14 into the sequence. Lastly, the solution of the Helmholtz equation for the function psi is given as psi is equal to psi suffix 0 in multiplication to jn as a function of kcr cosine of n phi into e to the power minus j times beta suffix g into z here. So let us, this is equation number 15. So with this equation we shall be concluding this particular topic. So representing beta suffix g, we have considered the lossless type of the propagation here. By the next lecture we shall be continuing into the same chapter to see the transverse electric mode of wave propagation for microwave signal inside the circular waveguide here. So for more such information and the details, if you require, you can subscribe to Ekeeda channel. Thank you.